333. Okay. So equals the mole fraction of oxygen, and obviously 0.67 equals the mole fraction of hydrogen. Does that make sense? Those are the mole fractions. So if I want to calculate what pressure, for instance, what pressure is the oxygen contributing to this overall thing, and if the standard pressure is 1 atmosphere, well, it's just going to be 0.33 atmosphere, and this is 0.67 atmosphere. Does that make sense? If it was 9.7 atmospheres total, well, 0.33 times 9.7, that'll be the pressure of oxygen. The volume, 0.33 times the total volume is going to give me the volume of oxygen. 0.67 times the total volume is going to give me the volume of hydrogen. Does that make sense? Add the volume together, it gives you the whole volume. So that's how you can use a mole fraction to determine, to work around some of these things. So one of the equations, well, no. So you can do that one. I'm not going to do it. I don't want to do this one. You can do this on your own. It's too easy. This is the last thing I want to talk about. What do I have time? What time is class over? Oh, we have plenty. Oh, we can finish. I want to finish so we can review on Thursday. I want to do it quickly. So, all right, this one's kind of an easy thing. Collecting of gases over water. Now, the problem with doing experiments, look at this experiment. What they're doing is they've got a sample in a test tube. They're doing a reaction. The reaction in this case is probably generating oxygen gas. Now, how do you collect oxygen gas? Well, if you can do it underwater, you let the tube fill up with oxygen gas. The oxygen goes through the tube. Now it's underneath the water. As it comes out of the water and bubbles up, it goes up into this container that's sitting above it, like an upside-down glass. The oxygen goes up, and what does it do is it builds up pressure, and it forces the water level to go down and down and down. You can see the water level's a little higher, then it's much lower over here. Is that clear? You see what's going on? The gas goes up, pushes the water down. That volume you can measure. You can measure that volume of gas. You can measure it very accurately. So, the problem is, think about this for a second. What is in top of this container right here? Just tell me everything that, if this experiment is generating just oxygen, O2 only. So the oxygen bubbles up, forces the volume to get bigger. So what is inside this thing above that water level in there? Tell me everything that's in there. Go. Oxygen and water vapor. Very good. Not liquid water. Liquid water being a liquid, but water vapor. Any liquid has a vapor pressure. It's always evaporating a little bit. So some of the gas that's above this water is not pure oxygen. So we simply, all we have to do is subtract out the amount that the water vapor is contributing to the overall number of moles of gas in there, if you will, or the volume, find out its partial pressure, if you will. Take it out so we can use the actual value of just the oxygen, that's the volume of it. Does that make sense? So that's what we want to do. It's that simple. And it's really easy to do. You're simply going to do exactly that. Look at this question. It says sodium metal is added to excess water at 1.2 liters of hydrogen gas. We're going to do this one, actually. 1.2 liters of hydrogen gas is produced in the reaction, and it is collected over water. If the pressure in the room and inside above the water is 745 torr at a temperature of 26 degrees Celsius, what is the mass of the sodium? So, in other words, look at the equation. We took a chunk of sodium, dropped it in some water. A reaction took place. Hydrogen gas is produced and sodium hydroxide. We know the volume of the hydrogen gas produced. And we know the pressure. We want to calculate the grams of sodium that did it. So this is just like the problem we did before. Almost exactly, where I said calculate the number of grams of potassium chlorate to fill up 3-liter container. So it's the same kind of problem that we're just going to work backwards. The only difference is we've got to take out 25 torr from the 745. Now just think about it. This pressure that is being exerted by the gas is 745 torr that's over the water. Well, of that 745, 25 torr is from the water vapor. So get rid of it. 745 minus 25, that's going to give me the pressure just of the gas, the hydrogen gas that was collected. So that's the number you're going to use to solve this problem. Let me just see what's going on after this. These are all definitions for the most part, yeah. Definitions in one equation. So let's do this one. I want everybody to work, because these are the big problems. I want you to work on this problem. And I'm going to get somebody. You all better get it. I'm going to randomly choose somebody this time, and you've got to get this answer. work together with somebody right next to you. I see a lot of dead faces in here. Faces that look like, what the hell are you talking about? The pressure of the hydrogen gas on the side. So this whole idea is just having you remember that if you do collect the gas over water, you got to take into account that water is producing gas. You got to get rid of it. So by subtracting out the pressure that water produces, then you're getting the pressure only from the gas. And use that number. Then it's just the same problem we had earlier. Yeah. 764 is 1 atmosphere. Absolutely. If you're using the ideal gas equation, you have to have all your units in atmospheres, liters, Kelvin, and moles. They have to be. So I want to know what is the mass of a chunk of sodium that is going to produce that result. 1 gram, 2 grams, 20 grams.
Hello. Can you hear me now? This is stupid. Get on it. Seth, please come to the principal's office. Bueller. Bueller. Bueller.
Raise your hand when you got an answer. I'm not going to pick on you. I just want to see a good show of hands. All right. You better be right. You got it. Everybody work. Pulling up the thing with you. What's the very last row back there, guys? J. And what's the seat number on the far end? What's your seat number? Yeah. Anybody that's on the far end? 27? 30? 28? What's your seat number?
30.
32.
I'm 30.
32. All right, here we go. I know it's going to be 8. So you know what? That's not fair. That's not fair. I agree. I don't know why I always pick the first one. I am D. D's fair. A, B, C, D. D is good. D. 7. No, it's that person who's not there. So it comes to it. You got an answer. What about Liz? Natalie. Yeah, you're really close. try it, Liz. I'm gonna work it out for you. I mean, Natalie. I'm sorry. I'm gonna get it. 2.19. This is Natalie. We'll call you Nat. Okay, so 2.19 grams. Is that what you said? Okay, so let's look at it. The equation was sodium plus, what was the equation? Two NOx. Okay, so there's the equation. This is what Natalie says. We're going to go find it. Now, one of the information it gave us is, I think, 745 torr, and then we got to subtract 25 torr. Now, you remember why we're doing that, right? You remember why? Because that gas, that pressure, you can measure with a pressure gun, 745 torr. Well, that's not only coming from the hydrogen. It's also coming from some of the water vapor. So we got to subtract that out. So 745 minus 25, 720 torr. Now I'm going to convert that to atmosphere. Divided by 760, 0.947 atmospheres. Okay, so 0.947 atmospheres is the pressure that's in there. So then we want PV equals nRT. We need to know the number of moles that was produced. So N is PV over RT. Pressure, 0.947 times the volume of, what did they give us a volume in there? 1.2 liters divided by 0.082 times the temperature. What was the temperature? 299 Kelvin. Everybody watch me. These are test questions. 0.947 times 1.2 divided by 0.082 divided by 299. 0.0464 moles of H2. Now, does everybody know where I got that from so far? Right? All I did was calculate from the pressure of the hydrogen. I got the number of moles of hydrogen. PV equals nRT. Once I got the moles of hydrogen, 0.0464 moles of H2. Stoichiometry, 1 mole of H2, 2 moles of sodium. 1 mole of H2, 2 moles of sodium. 1 mole of sodium is 22.9 grams of sodium. So I do the math, and is that what you did? Let me do it. 1064 times 2 times 22.9 is 2.12 grams of sodium. Liz said 2.19 grams, which would have been wrong on my part, because I know what you did. You forgot to take the 25 away, didn't you? She used this number, 745, and didn't take that away. So it does make a significant difference. So make sure you take that into account. True. Is that clear? Yes. Any questions about that? That's a good question. Did you put your book up? I heard somebody put their book up. Yeah. Hello, Liz. Yeah, I remember you're Liz, and that's Natalie. But there's an Allison Beach in here somewhere. Where is she? She's in the office. Where are you, Allison? Comes to the office. I know, it's weird, but she was in the office. Where is that young lady? I'm not going to pick on you, I just want to see where you are. Is she not here today? She was just in my office right before I walked over here. Said, I'll see you in class. No, well, it's definitely this class. All right, any questions about that one? Let me see where we are, because we're almost done. I mean, we got 4 more minutes, but the rest of it, this kinetic molecular theory of gases, I'm going to talk about it, but I'll wait till, don't be putting stuff up yet. But I'll be talking about it. There's a couple of equations like this one, really simple equation. It talks about the speed of gases. I want you to kind of look at it ahead of time, so I don't have to spend a lot of time on it. And we'll talk about diffusion and effusion, and another really easy